Hello everyone, my name is Kyle McNeese and welcome to the Atmospheric Sensor Node with Remote Display Capstone Prototype presentation. Today I will cover the project description, project objectives, first prototype, fabrication, the testing phase, results and discussion, our timetable, and then any references I've used throughout this project. The project description is to design and build two nodes that communicate over Wi-Fi. The sensor node measures atmospheric data and hosts a web server, and the display node requests the data from the web server and displays on an LCD screen. For our project objectives, I aim to measure sensor data remotely, utilize Wi-Fi communication between microcontrollers, optimize power consumption for battery-powered devices, and write a technical report on this capstone project. Our first prototype is accurate within plus or minus 1 degree Celsius, plus or minus 3% relative humidity, and plus or minus 1 hectopascal or 1 bar, and it maintains a 24/7 web server, and the battery I'm using for the sensor node is a 20 amp hour battery. Figures 1.1 and 1.2 below show the schematics for each node. So shown is the ESP32 and the sensor and where it connects to the ESP32, as well as for the display node, the LCD backpack and LCD screen, how they connect to the ESP32 as well, and notice the 5-volt difference on the display node compared to the 3.3 volt on the sensor node. This is important because the LCD screen is a 5-volt logic system and ideally should be powered by at least 5 volts. Figure 1.3 here shows both breadboards, both nodes. Below here is the sensor node. Right here is the BME 280 sensor connected to the ESP32. I've also added a button here for testing purposes. Anytime I press the button, it automatically takes a measurement and uploads it to the web server. And then up here, the longer breadboard is the display node. So here you can see how the LCD screen connects here to the LCD backpack, and then it has 2 wires coming out for the data and clock lines, as well as the power and ground. And notice the blue light here on the ESP32 microcontrollers, that indicates a Wi-Fi connection, which has been very helpful when troubleshooting connection issues. For the testing phase, I will be running overnight tests for the sensor node, and I will be purchasing inline ammeters for both nodes. I have already done both of these things, and the sensor node did maintain a 24/7 web server on the second and consequent tests, and data was able to be fetched and was readable. The sensor node uses roughly 55 milliamps, while the display node uses roughly 95 milliamps, which results in roughly 363 hours of sensor node runtime off of one fully charged battery, specifically the 20 amp hour battery mentioned previously. And the display node is a little unique in that I only have to turn it on when I want to see what the temperature, humidity, and pressure is. So we can somewhat ignore the amount of power this draws. The bigger challenge is going to be optimizing this 55 milliamps that the sensor node is using, because that requires staying on much more often than the display node. So here's our timetable. I have been able to stick to the timetable, and we are in weeks 7 and 8 here. So we are in testing phase right now. After this, I will be making tweaks for the final prototype before finishing this class. Here are 2 references that I've used. The first one being a tutorial on how to use a BME 280 sensor with an ESP32 using the Arduino IDE, which is the Integrated Development Environment. That's where I've had to write all of the C++ code. And then lastly, This last-minute engineers reference here is mainly for the pinout because the ESP32 microcontroller has specific pinouts, and not every pin can be used as a general purpose input-output. They have specified functions. And that's it for this presentation. I welcome any questions you may have. Feel free to get a hold of me. Thank you. Bye.